Black holes. A star came out of its main sequence, and then it started to shrink because on the inside there's no nuclear fusion happening with hydrogen pressing together to form new helium having an outward force. It shrinks, and then it shrinks more and more, and then it becomes the red giant phase, and there it is able, because it had shrunk more and heated up more through the shrinking together, having 100 million degrees, and now the helium can be formed together to form carbon and oxygen. Again, an outward force. The outward things are blown away, and now we're having just core standing basically there. It's just consisting out of this ash of helium or carbon and oxygen, and it cools down, and it goes completely together. So first it goes completely together until the shells of the atoms are standing completely together. And now we can't move anymore. It cools down, no movement, no heat. It just cools down and gets darker over hundreds of millions of years. If that big sun at the beginning had more than 1.4 times the size of the sun, so a bit bigger than the sun, then the Houth pressure of the core is too big, and these shells of the atoms break, they shatter. And now it doesn't stay a peaceful white dwarf, just all standing like that as degenerated gas, just standing like that forever and ever. They shatter. And now the electrons on the outside of the shells are fusing together with the protons on the inside of the atom and forming new neutrons. And we're having a neutron star. And now it has already shrunk massively. It can shrink again 1,000 times more, and it goes really, really close. It's still a few kilometers, but it goes very close together. And that is a neutron star. So the whole thing consists out of neutrons, all shrunk massively together, completely shrunk together, a few kilometers, turning incredibly fast and emitting light beams and so on. But what happens over the black holes? That happens if they have more than 1.4 times the solar mass. So the shells are shattering, it doesn't stay a white dwarf, it becomes a neutron star. If the sun was at 1.4 times as big, but more than 3 times as big, then these neutrons don't hold anymore, and even they shatter. So these shells had shattered in white dwarfs, becoming neutron stars, and now these neutrons themselves are also shattering. And now it just shrinks together until it has zero size anymore and infinite density. So the Houth sun, or at least the core of it, had shrunk down to become a white dwarf, and neutrons are just neutrons, and now the neutrons have shattered, and the whole thing becomes down to zero size, but it has infinite density. All is pressed out of it. And it has an incredible gravity set, the whole gravity set, and it pulls everything in, even light. And that is a black hole. It's just the sun going completely down together to zero size, infinite density, an incredible gravity pulling everything in, letting nothing out, even not light. That is according to Mark A. Garlick's Cosmic Mechanics book on the page 52. Hi and welcome. I'm trying to learn space science or helio science, I don't know, black holes, and after we've done it, we're gonna do hip training. And if you participate in the hip training, then it's really honest, helio science. It's space science, but it's part of the series what happens to stars, so helio science. Black holes, light traps. White dwarfs and neutron stars are certainly awesome, but a stranger fate awaits the universe's heaviest stars. White dwarfs are stable if they are less massive than about 1.4 solar masses. They say the white dwarfs, these are basically white dwarf stars are made of helium or carbon and oxygen, the products of nucleosynthesis. They are exceedingly compact. Once a star leaves the main sequence, its existence is a constant battle as the core struggles to generate enough energy to balance gravity. For hundreds of millions of years, the core contracts. All its material will eventually be squeezed into a super-dense sphere. Essentially, the electrons are crammed so close together that there is no longer space together. So they're just very close together. And now the neutron stars, they are so close, pressed together, that not just the electrons on the shells of the atoms on the outside are pressed together, the outstanding electrons, but also inside of the nuclei, the protons and the electrons, they have fused together to additional neutrons. Therefore, neutron star, they're basically just neutrons in it. The neutrons inside the nuclei are still neutrons, and the electrons from the outside of the shells, with the protons in the inside of the nucleus, were pressed together, one electron, one proton, another neutron. So the thing is even more compressed. And that thing is very fast turning. and it can emit on its axis magnetic radio beams of light and radio energy as pulsars. Okay, black holes. White dwarfs are stable if they are less massive than 1.4 solar masses. So if they had the mass of the Sun, they are pretty much close pressed together, but they are stable. The pressure is okay. The electrons are staying pressed together, like snow pressed together. Any larger and gravity, if you press things together, do that then get hotter? What if you press snow or ice so much together? Does it when? Yes, it happens. If someone goes with I really adjust again. If someone goes on ice, running with whatever it is, then the ice is melting at that point because of a strong pressure. Basic question is, okay, let's formulate it differently. If the Hulk would make a snowball, would it melt in its hands? Any larger and gravity overwhelms the pressure of a degenerated gas and the ions shatter, forming a neutron star. So if the pressure is bigger, the gravity bigger, then it overwhelms the pressure of a degenerate gas and the ions shatter. The atoms shatter and they become ions. Now there are ions. I don't know why it's not ions, because they were ionized in the phase previously already in the main sequence, I think already, or even previously in the meteoric phase. Okay, whatever, they are shattering, becoming a neutron star, they are pressed even more together. They're no longer standing with the outstanding electrons to the sides of the shells around them, they're pressed together, and now also the more pressed together. Neutrons are crammed against each other. The star is essentially a city-sized subatomic particle. By saying it is in essential just the one single atom, to be, let's say, because they're all pressed together, all to become one neutron. It's completely full of neutrons. Neutrons are, these stars withstand their own gravitation because there is no space between the neutrons, but only up to a point. Okay, they can stay like that. It's all pressed together. First there was inside the nucleus, protons and neutrons, and on the shells the electrons. They are completely pressed together, and all these shells are standing against each other. That was a white dwarf. In a neutron star, the gravity is stronger, they're pressing together and falling together, and even the protons and the electrons on the outside becoming new neutrons. The whole thing is just one singular big neutron, basically. Or just many, many neutrons. That is, I think, more accurate. No, but the thing holds. It holds together, all full of neutrons. But now the pressure gets stronger. What will happen now? In neutron stars weighing more than 3 solar masses, so if the force is more than 3 times as big or something, we say, the neutrons splinter, and then nothing known to science can stop the star collapsing indefinitely. It shrinks until it has 0 size and infinity density. Only its incredible gravity remains. These exotic stellar corpses are called black holes. So they are shrinking to 0 size, so they don't have a size anymore. But they are incredibly dense. There's very, very much pushed together onto nothing. But it keeps its full force of gravity. And that is a black hole. On Earth, when you throw a ball up, gravity slows it down. It reverses the direction and falls to the ground. So you throw a ball up, it reverses the direction from going upwards, downwards, and falls onto the ground. If a ball travels fast enough, about 11 kilometers per second, it would overcome gravity and escape into space. So I'm saying, if you would throw a ball with 11 kilometers per second, so that means in just 1 second, it would go 11 kilometers away. So you would have to throw it very hard. Then it would overcome the gravity of 100 kilometers gravity, basically, and it would float up into space. A black hole gravity is so powerful, however, that no object would ever escape it, even light, which travels at the universe's ultimate speed limit of 300,000 kilometers, is held down. Black holes emit no... Okay, they're basically saying, if you throw a ball with middle force that flies 5 meters high, if you throw a full force, maybe 10, 15, maybe 20 meters high, but it still comes down. If you throw way much harder, maybe 50 meters, maybe 100 meters. If you shoot with a gun into the air, I don't know how high, a few hundred meters. But basically like that, and you can take a stronger gun and so on, and you can go maybe a kilometer high or something. But then it would still fall down. If you would be able to shoot something with 11 kilometers per second, and then it would go up into space. I don't think there exists any guns which can do it. Maybe rockets, whatever. But they have an external push. So basically, if you have a very, very powerful thrower, catapult, or very powerful rifle, I don't know which rifles like that exist, then you could overcome it and you could come into space. They're saying that way someone could overcome the gravity of the Earth. The gravity of a black hole is much stronger. Even if it would have 300,000 kilometers per second, so not 11, but 300,000, like light has it, it would still not be strong enough to go away from the black hole and go. Because black holes are so incredibly strong pulling it. Black holes emit no radiation, including light of any kind. This is what gives them their name. They are not emitting light, not even no radiation, no light. They are just black. There comes no light out, so they are black. And no other types of radiation because it's all pulled in. Astronomers have found many cases where an invisible object, a suspected black hole, orbits a normal star. So something which is suspected of being a black hole is orbiting around a normal star. The black hole's gravity and it all was just a too big star. So it's not that these black holes somehow exist or something, or that it's just that out of something has something differently grounded. Now, the black hole's gravity warps its companion into an egg shape. That makes sense? So it goes around it, and just like the water, the tides goes a few meters, 50 meters or something in some regions. So let's say 5 meters or 2-3 meters to it. The water always around. Is it like that? Someone is doing it like that. And the water goes always to it, and the water has been going into it. So the water has been away from the coastlines a few hundred meters or even a few kilometers in some regions. And the water is bulging also 5-6 meters or something to the moon. But now where these black holes are circling around another object where they are pulled completely into an egg shape, the whole planet. Not just the water, 3-4 meters, but the whole planet. How much is actually the moon pulling the Earth to the side? The black hole's gravity warps its companion into an egg shape, pulling gas from its atmosphere. Just before they vanish into that gaping maw, the gases are so hot that they shine brilliantly in X-rays. So we're saying that there are some places where black hole is circling. Why the black hole? Why not the other object circling? That is, I don't know. Now these gases pulled in by the black hole circling around the other object are shining brilliantly in X-rays. This is a phenomenon we met earlier, where gravitational potential energy is converted to heat as the gases flow inwards. I don't really get it, why it wasn't explained why, but basically it is for potential energy because it is an existing gas which can fall over. Now it's made to fall over, it's pulled in, it gets faster, strong, whatever, and now it is radiating brilliant X-rays. Astronomers detect this and infer that a black hole must be there. So we can't see the black hole, but we can see that there are gases which are then falling over into something, and while they do it, they are emitting X-rays. They can measure its mass using the laws of motion and be confident it is a black hole if it is heavy enough. Basically, if it's like what are these things even called? These vacuum cleaners. If they're pulling strong enough in, then it is a black hole. We will meet some of these binary systems in the following chapter. Okay, we're going to talk about binary systems. We're going to talk about stars who don't have a planet circling around them, but a black hole. That was the Heliology part. If you were here for Heliology, you can go back to the next part of Heliology, where you're going to read on. If you stay here and participate in the Hiptraining, then as well as the others. Feet are standing together. One toe to the outside, other toe. Heels, heels, and so on. As far as you can go. and then back again in. This time stay in the knees with the legs. Up again. A bit further apart, down, flex the legs, press them together, straighten one leg. Bend it again, other leg, straighten it, and bend again, and up. A bit further apart, down, flex, press together. Over to one leg, the other side. Bend it a bit closer together, press to the outside. And one leg, and to the side, breathe in. Middle and down, other leg up. To the side, breathe in. Middle and down. And one leg to the side, lift it off the ground, place it again onto the ground. Other side. One hand on tummy, one on lower back, and lift one leg up in a straight line. Flex foot. Try to bring the leg higher. And pull the toes in. And bring the leg up. Other leg. Stand good on one leg and turn over. Down into the knee, bit to the outside. Other leg. Turn over. Down. Turn over. And one. The heel onto the ground, don't do it if you're pregnant. Lift the heel off the ground, place it again onto the ground. Other side. Toes up and onto the outside, breathe in the arms up. Short sink down. Hands onto the ground, come back up, and roll slowly with the round back. Up again as we top the backward shoulder roll, another round in the arms up. And sink down. Hands into the ground, neck up, roll slowly up, backward shoulder roll at the top. Stand good on one leg, arms to sides, and bring the leg back and the upper part of the body down. And again, and now pull the knee in and out. And back, other leg. Back, another time, and pull the knee in. And legs to sides, breathe in and out. And breathe out. And up. Out. Breathe in and cross the legs. Breathe in and out. That was the hip training. I thank you very much, and until the next time.